Hi, welcome. In this video, we're going to talk more about how to identify non-regular languages and then get into context-free languages. All right, so at the beginning of the semester, I showed you this table, and this is the hierarchy of languages and automata and the grammar production rules that coincide with those languages. So we started with regular languages, and we will start learning about more languages throughout the rest of the semester. And our next set of languages we're going to start talking about are context-free languages. So let's talk a little bit more about languages in computer science. Obviously, languages allow communication between computers and machines, and between people and machines. And our next set of languages, we're going to talk about our context-free languages. And this course is about the study of languages and automata and the theory of computation and computability and, Turing's thesis and the hierarchy of languages and the relationship between these languages and the automata that accept the languages and practice using state machines. So that's what we do in this class, but all of this study does form the basis for computer languages that are used. So we have other courses, computer languages, and we also have, there are also courses on compiler writing that use a lot of the, that build upon the stuff that we have learned and connect the dots of the stuff that we are going over in this course. All right, and just another thing about state machines and games. Obviously, when you play games, you are going from one state to another based on the choices that you make, similar to the way we are doing our state machines. We are using finite state machines to understand infinite languages. So we've been making DFAs and NFAs, which have a finite number of states, and some of the regular languages that we've drawn with our state machines, or that we've talked about, or that we've studied, are infinite languages. We are using a finite number of states to talk about infinite languages. So if you use a finite number of states for infinite languages, you're going to have a cycle in your graph. And then using these machines help to recognize the different types of languages. So let's go back to our languages and our automaton and our grammar production rules. So we spent quite a bit of time on regular languages and DFAs and NFAs. We learned that the grammar production rules for for regular languages are that you have to have a right linear or a left linear grammar for a regular language. The next set of languages we're going to talk about are context-free. Context-free, the automaton for that is called an NPDA, or non-deterministic pushdown automata. So the big thing that we're going to be adding now is we're going to be adding a stack, and we're going to be able to store some information, where a DFA only knows about the state that it's in. You can't count anything, you can't keep track of anything, you just go, you consume a symbol, or you do a jump, a lambda transition, and don't consume a symbol, but you don't count how many times how many A's you've consumed, or how many or like the string you've consumed so that you can copy it again. You can't do that with a DFA or an NFA. All you can do with a DFA or an NFA is go from one state to the other, and you can allow some symbols to occur in arbitrary or an infinite number of times, and then you just put a cycle in your graph. And then after that, we'll get to context-sensitive languages, following the Turing machine and recursively enumerable languages. And you should Google about Turing and Turing's thesis. We will be talking about that later in the semester. And here you can see that regular languages are a subset of all of the other languages. And so we spent quite a bit of time, just being able to understand what a regular language is. And now it's time to identify non-regular languages. All right, so the first thing we'll talk about is the pigeonhole principle. The pigeonhole principle says that if you have a bunch of boxes and you have more items than you have boxes, then at least one of your boxes is going to have more than one item in it. So if you had 3 boxes and 4 items, you can't evenly distribute 4 items into 3 boxes. One of those boxes is going to have 2 items in it. So the pumping lemma uses this, but it basically is saying that if you have a finite number of states and an infinite language, you're going to have a cycle on one of your states, at least one of your states, right? So if you have a finite number of states and you're going to allow an infinite, like a to the n b, where n is greater than or equal to 0, that means you're going to have you're allowing an infinite number of a's. Your DFA is going to have a cycle. And it just says that every sufficiently long string in your language can be broken into 3 parts, and that middle part is going to be a cycle, and if you pump that, you're still going to have strings in the language. So I'm going to, I put these videos from Lydia, which I found on the internet, and I thought they're very, they're little cartoons. They explain this, you know, in a, try to help you to see this, because this, this long theorem, it's not long, it's short, but this theorem, the explanation of this theorem is seems very complicated, but the truth is, if you just look at it and you look at the y is the part that is pumped. So if I can pump a symbol or a or a few symbols in my language, and when I pump them, the resulting string will still be in my language, then it's a regular language. But if I pump it, well, we're not guaranteed it's a regular language. But so what you want to do is you want to take a language that you're having a hard time building a DFA or NFA for, and so you're thinking, okay, this is probably not a regular language. Then you use the pumping lemma, you assume it's a regular language, and then you use the pumping lemma to show that it is not a regular language. So you only do proof by contradiction with the pumping lemma. The pumping lemma is not going to clearly state that a language is regular. How you're going to know a language is regular is if you can build a DFA or NFA for it, or a regular expression. Regular expressions would have a star on the part that can be pumped. A DFA or NFA has a cycle on the part that can be pumped. Okay? You can't use the pumping lemma to show that a language is regular. You can't, you use the pumping lemma to show that a language is not regular. You show that if I pump this, after I pump it, the resulting string doesn't follow the rules of the language. So you use the pumping lemma to show that a language is not regular. You don't use it to show it is regular, and you don't use it for any finite language, because you can do a DFA with a finite number of states for a finite language. Even if it has, even if it's large explanation, you can still, it would just be a large DFA or NFA. So here's an example of a regular language. This is a language where a to the n b, where n, any number of a's followed by one single b. So we have 2 cycles in this DFA, but the second cycle we don't care about, because the second cycle does not lead us to our accepting state. So we could do this with an NFA. I just have a DFA to be complete, but this could be built with an NFA, because there's no reason to deal with any A's and B's after we've gotten our final B. So you can have any number of A's followed by one final B, and the part that is pumped, the Y in this, would be an A, would be the A. So if you have an infinite regular language, you have to have a cycle in your graph, because you cannot build a DFA or NFA for an infinite language without a cycle. It doesn't matter where the cycle is, it's just there's going to be a cycle somewhere. The symbol on the cycle transition can be pumped an infinite number of times, and the string will still be in the language. That's what pumping is. You're just A, B is in this language, A, B is in this language. 1,000 A's and 1 B is also in this language. I can keep pumping that A, and I'm still going to produce strings that are in this language. So if you go back and read this again, let L be an infinite regular language. There exists a positive integer m such a way that, okay, so you pick a string. So W means a string. You pick a string in your language. The size of your string must be greater than or equal to m. So you have this number m, and then you pick a string in your language that is greater than this number m. Then you decompose your string that you've selected into 3 parts. The first part is the x, the second part is the y, the third part is the z. Okay, so then there are some rules. The first part of that, the xy part, must be less than or equal to this m, this arbitrary number m that was selected. The size of y must be greater than or equal to 1. That means you can't pump the empty string. W does not have to be, W can be the empty string, Z can be the empty string. But technically the X would be any part before the part that's pumped or any part before the cycle in your graph. The Y is the part that is pumped, the cycle in your graph, and then the Z is the part that leads you to the accepting state. So that's breaking that down, and it's just saying that every sufficiently long string can be broken into these 3 parts, and the middle part you will still make strings that are in your language. So let's I broke it down here again. So W is the string in the language. The size of W must be greater than equal to this M. Your string will be broken up into 3 sections, X, Y, and Z. X is the section before the string is pumped. It can be the empty string. Y is the section of the string that is pumped. It cannot be the empty string. And Z is the section of the string that takes you to the accepting state. Then there's just a couple other rules. I just already said the size of Y must be greater than or equal to 1. That's the string that's pumped. And the size of XY must be less than or equal to M. The pumping string must be in the first M symbols of this string that you've selected. All right, so you can read it again. Keep in mind that the pumping lemma cannot conclude that the language is regular, but you use it by contradiction. You say, I have this language, and can I pump? And if I cannot pump, then I can conclude that it is not regular. All right, so this is a regular language. I just put this back up here for in case I wanted to talk about it again. This is also a regular language. So if you take a look at this language right here, we are pumping. We have actually, the union of 2 languages, but we know that the union of 2 languages is still a regular language. So we have a bunch of parts that we're pumping, but if you pump the A in the first, in the AA part, you will still have strings in the language, and in the bottom part you can pump the A's and pump the B's. All right, so here's a little bit more about transition graphs for regular languages. If your transition graph has no cycles, then the language is finite. And of course, we already said all finite languages are regular. If the transition graph has a cycle, then the language is infinite. Every infinite regular language has a DFA with a cycle. All right, so this one happens to have a DFA with 3 cycles. It doesn't really matter. But if you have a cycle, then you're going to have, this is breaking it down again for you. Instead of using X, Y, Z, we have W1, the V is the Y part, and the W2 is the Z part. So you can break down your strings and you can pump. So you can pump as many times as you want, and you will still have strings that are in the language. The only thing also If your DFA has M number of states, obviously the cycle must be entered by the time you have read M symbols. That's why the size has to be smaller than XY. You can't hit the cycle outside of your states. If you have a certain number of states, you're going to have to hit the cycle before you complete those states. All right, so here's another example of a regular language with a cycle. We have this, the cycle is in the middle of this. I'm not using the M, X, Y, and all of that on this. I'm just demonstrating again that this is a regular language. We have an A and a B, and then you can have any number of A's or any number of AB's. You can pump the A's and the AB's in the middle, and you will still have strings that are in the language. So it's the same thing. All right. All right. So now we're going to talk about another regular language. So here is another regular language. Why is this a regular language? Well, we can pump our A's as many times as we want. So this is, okay, first let's look at the L language. This language says any number of A's followed by any number of B's, and then the last part, because this is a DFA, we don't care about, we only care about our accepting state, right? So we have any number of A's followed by any number of B's. So here you can pump your A's and you still are going to have strings in the language. You can pump your B's and you're still going to have strings in the language. Okay, so here we are now going to finally get to a language that is not regular. The language here that is not regular is A to the N, B to the N. So I'm going to end here and start work and make another video.